All right, last part of the chapter 5 involves, I'm going to give you a little demo first before we actually start our discussion. All right, I got 2 blocks here. They're both made of metal, and I'm going to involve some audience members here. I want you to touch both of those blocks and tell me which one feels colder. This one feels colder, he said. I want you to verify. Yeah. Okay. This one feels colder. All right. So I'm going to put these up here. Okay. This is the one that feels colder. And this one feels warmer. All right. I know it's hard to read that, but now what I'm going to do is I'm going to just put a little plastic ring on the top of these, and you see I put a paper towel here because it involves some melting of ice. I brought some ice from the freezer. I used to do demos with almost every lecture, but then our last chair, not the current chair, came in one time and said, you can't do demos because there's no running water, there's carpet, and there's only exits in the back of the room. So I can only use water under 80 degrees or household chemicals now in demos, but ice works. All right, so now I'm going to take an ice cube, and about the same size ice cube I'm going to get. It's a little hard to see. Let me see if I can turn the light off better. It'll adjust to the difference in just a minute. I think that's going to look better. All right, so now I'm going to take each ice cube and I'm going to put it on the tray. The top one feels colder, and the bottom one feels warmer. I'm just going to move the little ring up. So the ring is just so that as the ice melts, it's not going to run off. It does look alive, huh? It's moving because it's not a perfectly level situation here. So what do you see happening? What's the difference here? The one that feels colder is, in fact, melting the ice faster. In science, this is what we call a discrepant event. It's supposed to cause you to go, whoa, everything I thought was true maybe is not.
And that's chemistry.
That's chemistry, that's right. So which one would you say has a higher heat capacity, a specific heat? Each of these metals has its own heat capacity, right? Which one would have a higher heat capacity?
The top one.
The top one would have a higher specific heat capacity. Remember, specific heat capacity is a measure of 2 things. First of all, how much energy it takes to warm something up. So if you have a larger number, it's going to take more energy to change its temperature, right? Think about it like money. If it's 0.375 versus 0.18, 0.375 is going to require more energy input to change its temperature. But also you have to think about it like an engineer's perspective, that if it has a higher heat capacity, it's also a better conduit. It moves heat energy better than its counterparts that does not feel so cold, because which one is going to have larger particles in it? The one that feels colder or the one that feels warmer? Which one's going to have larger particles in it?
The warm.
The warm one. And how do we know that this one has smaller particles? Has a higher heat capacity, it has more particles in it, requiring more energy to heat it up, because every bit of energy you add is distributed amongst the particles, right? If I said, I've got $47, well, that seems like a pretty good amount of money. I mean, I could probably buy groceries for at least a week on that, because I'm pretty frugal, right? $47, but if I said, oh, I got $47 to give away to all my students, that's only $1 per student. You're not going to buy a lot of groceries with $1 per student, right? Okay, so that's the difference between energy and the amount of energy that, well, it depends on what you buy, right? When I was in college, it was ramen noodles and hot dogs. Those were my favorite things to eat. And ramen noodles you can do anything with. Boy, you get a little can of spaghetti sauce, you make some ramen noodles, you get spaghetti. Dress them up with little veggies and some spices and make them stir fry. Yes, hon?
So is it that even though the colder one felt colder, but it was a better conduit, and that means that it's gonna move heat through the ice cube better, faster?
Well, let's think about it. Here was the metal, right? And here was the ice. What was the metal doing with Q? Moving Q from where?
From the ice to the surroundings.
Not from the ice. It was not going from the ice.
Into the ice?
It was going into the ice.
Yeah, the ice was melting.
Right. So Q was going into the ice, but where was that Q that was going into the ice coming from? The metal, and ultimately from the surroundings, right? So the metal was providing a conduit of heat energy, pulling heat energy from the surroundings. Of course, the metal got colder than it was initially, but it was very efficient at pulling heat energy and pulling that Q from the surroundings through the surroundings into ice. So was this an endothermic or an exothermic reaction? Endothermic, right? Because we had to add heat energy into the, and this is called the heat of fusion for ice. And I believe you are doing a lab in this class for the heat of fusion for ice. Now, in the literature, the heat of fusion for ice, I looked these values up. Let's see, what does it tell us? It tells us the heat of fusion for ice, I found one value, 80 calories per gram. And then I found another value, the heat of vaporization. All right, that's the heat of fusion for ice. What calories per gram? What does that tell you about the units? Heat of fusion. What's actually happening here? We're changing it from a solid to a liquid. So there's no chemical reaction. It's a simple physical change. It's a phase change. But in order to change phase, it requires energy. At the outset of our discussion in this class, remember I talked to you about a lab that I used to do with my high school students, and we would generate a heating curve. We would start with ice, right? And we would take the ice, frozen in a beaker, and over time, we would heat the beaker up, and if we graphed time versus temperature, for that graph we would say, okay, here's 0 at freezing point, and 100 degrees is the boiling point. We would start the ice, we would warm up the ice, then the ice would melt, the temperature would not change while the ice was melting, so it was all a solid here. Here it was a solid going to a liquid. Once it completely turned into a liquid, at this point everything was liquid. Once it was completely a liquid, then the temperature could rise again and it would be a nice consistent curve. This is all as a liquid. Once it reached the boiling point, the temperature would level off again, and it would level off until what happened in the container? It would all be gone, right? Now if I had a closed system, could I in fact increase the, if I had like a pressure cooker, if any of you, maybe none of you have ever used a pressure cooker before, but my mom used to use a pressure cooker all the time to make pork roast and sauerkraut. I still can't stand the smell of that cooking. It just grosses me out. But she would use a pressure cooker and it'd cook all day. And a pressure cooker is a sealed container that holds the steam in, so you can actually get the steam hotter than 100 degrees. Because steam, when it vaporizes, is 100 degrees. But if you keep it inside the pressure cooker, it can get up to temperatures of hotter than 100 degrees. And that's why a pressure cooker is helpful, because you can get temperatures inside of it because it is a closed system above 100 degrees. So this is the liquid to gas phase change, and this is when it's completely a gas. Well, we've got some values here that we need to talk about. One of the first values is this one here, which is going to be a lot of what your lab is about. That first plateau is called the heat of fusion for ice, right? So this is the heat of fusion right here. I want you to label this heat of fusion. And that's generally some energy per unit of either things like either grams or maybe sometimes moles. So I've seen heat of fusion values in calories per gram, I've seen them in joules per gram, I've seen them in kilojoules per gram, I've seen them in kilojoules per mole. I like kilojoules per mole because that's nice and consistent with our enthalpy values. And you can talk about the enthalpy exchange during phase changes. And the heat of fusion is an enthalpy for a phase change. So I like to use units of energy, which is kilojoules, and moles, which tells me how many pieces I'm dissolving. There's also enthalpy of vaporization. Enthalpy of vaporization, if you're looking at it, let's see, this one was, heat of fusion was 60 calories per gram, or no, 80 calories per gram was our value there. Heat of vaporization is, I think, 540 calories per gram. Well, holy smokes, how come it's so much more to vaporize 1 gram of liquid than it is to melt it? It's like, what, 5 or 6 times as much? What's that? Requires a whole lot more energy, but how come it requires so much more energy? You got hydrogen bonds going on, not the hydrogen and oxygen bonds that hold water together. Remember, it's not breaking up into hydrogen and oxygen, because if that were true, we'd all be exploding every time we cook over a gas stove, right? It doesn't happen. But the hydrogen bonds, the bonds that are polar water molecules, they're kind of like magnetic. Water molecules are magnetic. this discussion is generally in your textbook, Brown LeMay. This is the only thing I don't like about the textbook is they save this discussion for chapter 19, which is what you will get into when you get into Chem 152. And the reason they put this discussion in chapter 19 is because it's based on what's called intermolecular forces. Intermolecular forces are the forces between molecules, or hydrogen bonding, the thing that makes them kind of magnetic. And intermolecular forces changes the boiling point of substances. That's why water has a ridiculous high boiling point, because it has really high intermolecular forces and it takes a lot of energy to break it. So, for example, if I wanted to calculate the enthalpy of some amount of water to change it from, let's see, my temperature initial, say I'm going to have 15 grams of water. And my initial temperature, I'm going to start it out at, let's see, I've got ice. Well, we're going to say it's at 0 degrees. And it's all a solid. And I got 15 grams of water. And then I want to get it to a point of, let's see, I want to get it to 80 degrees Celsius. All right. So I've got to melt the water, and then I've got to increase the temperature. So if I was looking at a journey, I'm starting right here, right? I'm starting with something that's completely a solid, so this is my start. I've got to take it through the energy change to melt the solid. Then I've got to take it through another energy change to get it from 0 degrees all the way up to 80 degrees, which is my end point up here. So they're going to ask you, what is the enthalpy required, or what is the energy necessary to take 15 grams of water and make it go through that change. All right, so calculation, and there is a problem like this on the exam, and this is something that you're going to be using, I think, next week when you do heat of fusion or whenever you guys do that lab. All right, so if we look at this in terms of a calculation type of problem, we say that we've got two legs of the journey that we have to do calculations for. I've got a melting journey and a heating up the water journey. And I know that the melting journey, I've got 15 grams of water, 15 grams of water. And I know that the heat of fusion for ice is 80 calories per gram. But I need my enthalpy value, my H value. I need to know what it is in joules or kilojoules. So this is going to be a practice in doing some unit conversions as well. What could I do to figure out the energy that's just going to get me from this to this, to melt the water? I could use Q equals MC delta T, but is there a temperature change here? There's no temperature change, right? There's no temperature change, so we could kind of eliminate that idea from there. So I could take the mass times the energy term. If I took the mass times the energy term, 80 calories per gram. What's 15 times 80? Somebody with a calculator. 1,200, thank you. Calories, but I need it in kilojoules. So what's the equivalency there? 4.18 joules is equal to 1 calorie. That's a piece of information you should know. Hopefully, now you do. 1 calorie is 4.18 joules. So then that would give me my, what's 1,200 times 4.18?
5,016.
Joules. All right, so that's how much energy it would take to melt the ice, but that's not including the amount of energy to go once it's completely melted all the way up to 80 degrees. So then I could use the full Q equals MC delta T for that part, right? So I have to go up this thing, this slope. So what's my mass here in the problem? 15 grams. What's my C? 4.18 joules per grams degrees Celsius. And what's my delta T? 80 degrees. Once I calculate, what's my Q there? $15 times 4.18 times 80 is 5016.
Yes.
And that's going to be joules. All right, what?
Yeah.
Nuh-uh.
Ta-da.
Well, you know why? Here's the magic number. Because I picked
80.
80, and that was the temperature change too. So it won't always be the same value. Okay, normally they're very different values, but because I picked an 80, if I had picked a 70-degree temperature change, they wouldn't be the same, right? So that was my mistake, the math of it. They don't come out. So now, wait a minute, we're not done. So if I want to figure out the total energy necessary to go through that entire exchange, what would I do with the two Q values that normally would not be the same? Add them together, which would give me overall joules of energy, but we're not done yet, right? Overall joules, wait, so 5016 joules, 5016 joules. 1032? 10.
32.
Thank you. 10,032, you're right. There we go. All right, but that's joules, but I wanted to change to kilojoules. So 1, 2, 3. So 10.0 kilojoules of energy. All right, so that's just an example. So for example, what if they wanted you to vaporize it and get it all the way completely to a vapor? What would you have to change? You'd have to figure out the energy exchange necessary for this portion of what you're doing. They also, in your lab, they're asking you to calculate the heat of fusion. So, I know that in the lab, they probably just are going to turn you loose and say, figure it out. If you have a really good set of notes, I'm going to tell you how to do it. This is the lab. What you got to do is you got to make yourself a coffee cup calorimeter, right? You got to put some water in the coffee cup calorimeter. There we go. You got to put some water in the coffee cup calorimeter. Does it matter how much you put in there? No. But you do got to know. And you got to know the volume of it. Because say, for example, and I'm just going to pick some number out of the air. I'm not expecting you to use this. What if you had 150 milliliters? We'll just say that that's what you use. Then you're going to pop an ice cube in there. Right? What's going to happen to the ice cube? You do not need to heat the water up. Regular room temperature water will do the trick. And it's going to melt. Right? So the ice cube's going to melt. What's going to happen to the water level as the ice cube melts? It's going to go up. All right. So let's think about where's Q going. Think hard about this.
From the water.
From the water into the ice. What are you going to be able to measure a temperature change for? Not the ice. You don't know. Do you know the ice is starting at 0? No, it could be a lot colder than 0, so you're going to have to assume that it's 0, and that might be part of your error, because y'all are going to have to assume that it's 0, but you know that it's not going to necessarily be 0. But what can we measure the Q moving? The water. You can measure the Q of the water, right? So the Q of the water would be what?
The volume or
150 grams times what? 4.18, our favorite number in this chapter, times what? Whatever the temperature change of the water was. So you got a temperature initial, then you got a temperature final. Your teacher's probably just going to say, figure out how to calculate the heat of fusion. You're going to have a nice plan already. You can just zip right through it. So you got the temperature initial, temperature final, figure out what your delta T is. That's going to go there, right? But then that tells you the Q that came from the water, and where did it go? Into the ice. You got to calculate the enthalpy of fusion. So that's going to be, what are the units of all enthalpy? Kilojoules per mole. Where's the kilojoules going to come from? Here's the hard part. What moles do I use? Not the moles of the surroundings. Where did the Q go from? It went from the surroundings into the, you want the heat of fusion of the ice. So what moles do we need to use here? Moles of ice. How could you figure out moles of ice? Make lots of stars around this T, because this is where people make the biggest mistake in this lab, is it's moles of ice. How could you calculate how many moles of ice you used? Can't weigh anything that's a liquid on those balances. Bzzzt.
It's, we gotta measure the difference of the volume.
Difference of the volume, right? Because you know how much water, and if you measure the amount of water exactly with a graduated cylinder, not a beaker or a flask, make sure you use a graduated cylinder, because that measures precisely. Measure the initial water you put in. It doesn't matter the size of the ice cube because it's gonna melt. And then if you measure the water when you're done, is it gonna be a larger volume or a smaller volume? Larger volume, and the larger the volume is going to be due to the ice melting. You know the volume of the ice melting, you know the grams. Can you not then change it to moles? Okay, so there's your plan. You're welcome. Yes. Well, because you're talking about the temperature change surrounding. So initial minus final would be temperature of the surrounding. And that's going to calculate your Q of the surroundings, but remember the Q going into I would temper this by saying heat diffusion with endo X right now.
I asked you because
Endo or X.
yeah. Are you I just finished my there's no more heat for this but calculus 2 is easier than calculus. Really? I saw that one.
Study guide for the next test has been posted. It's been posted the whole semester, so all you gotta do is access. It's in files. Study guide, review, whatever, it's in there. Yeah. I'll do that right in class. Water levels can go up.
Got it. So then that's how you get the gauge from that one is that.
Sometimes you can measure the surrounding. Sometimes you can measure once you know that, you know it's the same Q that came from the origin to the beginning, and you go transform it. You know, energy had to go into the ice. You can quantify the energy that goes into the ice because you can measure it. The water, you know everything about the water. Once you know that Q, that's the same Q that went into the ice. So the fusion amount of energy to melt the ice per mole is that transfer. And that's why in thermochemistry, thermodynamics, you have to really think about Q going from one place to another, because that's what helps you separate the system into rhythms. It's such a really difficult conceptual topic to talk about, especially at this point. You guys have had zero experience with this stuff, so if you are feeling uneasy, that's in good company because it's all new stuff.
Yeah, and then the delta T from that one, that's just gonna be based on whatever.
Whatever the temperature change in your cup is of the water. You guys can pick some arbitrary number of water. I always tell my students, let the ice cube melt. Don't take it out after some point.
Yeah.
So why do you find the molar mass of ice compared to, or like for the fusion, why do we find the moles of ice instead of moles of water?
Because when you're calculating the heat of fusion for ice, you want to know the amount of energy it took to melt how many moles, how many pieces of things you had that was left. Q went from the water into the ice. So when you calculate Q that went out of the water, that Q is the same Q that went into the ice. And when you calculate the enthalpy of the ice melting, it's Q over the moles of the ice. Because the energy went into the ice. And once again, this all relates to system and surroundings. And they have a pretty couple paragraph description of that and the theoretical part of it in chapter 5. But I would encourage you to read all that. Because this in chapter 5 really will help a lot of reading. Chapter 4 not so much, but chapter 5.
Is this all be under a test on
Yes, you'll have a problem, not the heat of fusion problem, but you will have a problem like where you have to say, okay, if something starts ice and you want to bring it to this temperature, you have to just on that kind of problem.
Yeah, like,
Do you have
like,
Snapchat?
like
I will post,
the
I'll
answers,
post a couple.
Yeah.
with the answers in classical and then.
Sure, then you can practice and make sure that you're doing it right.
Yeah.
That's a good idea.
Yeah, I'm making a couple more things about it.
Yeah, I gotta go through and dig some up from chapter 19, I think is where they usually. Hang on, let me shut this off so I'm not still recording my discussions with students.